delta-delta transformer can provide 120/240 volts and 120/208 volts from a 120/208 volt delta source. The X0 terminal on the transformer is the neutral of the 120/240 volt delta secondary winding. When connecting a 120/208 volt delta secondary to a 120/240 volt delta load, no neutral is used. The transformer is backfed to obtain 120/240 volts on the secondary. The X0 terminal on the transformer is not used and isolated. The distribution panel for the 120/240 volt load does not have a ground reference to any of the phases. The absence of a ground reference in the distribution panel makes it difficult to detect ground faults. If a ground fault occurs, it may not trip the circuit breaker, posing a safety hazard. In a delta system, the neutral point can shift due to unbalanced loads, transients, or other factors. This can result in overvoltages on equipment connected to the system. To improve safety and reliability, the following recommendations are made. Firstly, install a ground rod and connect it to the equipment grounding bus in the distribution panel. Secondly, consider using a ground fault circuit interrupter, or GFCI, or a residual current device, or RCD, to provide ground fault protection. And thirdly, monitor the system for neutral point shift and take appropriate corrective actions if necessary. Ground fault protection is crucial for safety in electrical systems. A ground fault occurs when an unintended electrical path is established between a live conductor and ground. This can happen due to damaged insulation, loose connections, or accidental contact with grounded object. Without proper ground fault protection, a ground fault can result in electric shock, fire, and equipment damage. The primary purpose of ground fault protection is to quickly detect and interrupt ground faults before they can cause harm. This is typically achieved by using ground fault circuits, interrupters, or residual current devices. GFCIs and RCD monitor the current flowing through the circuit and compare it to the current returning. If there is a significant difference, it indicates that some current is leaking to ground, and the device will trip, disconnecting the power. The National Electrical Code, or NEC, provides detailed requirements for ground fault protection in various types of electrical systems. These requirements vary depending on the voltage level, the type of occupancy, and the specific application. For example, NEC Section 210.8 requires GFCI protection for receptacles installed in dwelling unit bathrooms, kitchens, and outdoor areas. NEC Section 230.95 requires ground fault protection for service disconnecting means rated 1000 amps or more. In industrial and commercial settings, ground fault protection is often implemented using ground fault relays and current transformers. These devices monitor the current flowing in the grounding conductor and trip the circuit breaker if a ground fault is detected. Selecting the appropriate ground fault protection device depends on several factors, including the voltage level, the available fault current, and the desired level of sensitivity. It is important to choose a device that is properly rated for the application and that meets all applicable code requirements. Grounding is an essential safety measure in electrical systems. It provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and energize the circuit. Grounding also helps to stabilize the voltage on the electrical system and reduce the risk of electric shock. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding involves connecting all non-current carrying metal parts of electrical equipment to ground, such as enclosures, conduits, and motor frames. This provides a path for fault current to flow back to the source in the event of a ground fault. System grounding involves connecting one of the current carrying conductors of the electrical system to ground, typically the neutral conductor. This helps to stabilize the voltage on the system and reduce the risk of overvoltages. The NEC specifies the requirements for grounding electrical systems in Article 250. This article covers topics such as grounding electrode systems, grounding conductors, and bonding. A grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. These electrodes are connected to the grounding conductor, which runs back to the service equipment. Bonding is the process of connecting together all metal parts of the electrical system to ensure that they are at the same electrical potential. This helps to reduce the risk of electric shock and fire. The NEC requires bonding of all metal enclosures, raceways, and equipment grounding conductors. Neutral point shift can occur in delta-connected electrical systems due to imbalanced loads, transients, or other factors. In a delta system, the voltage between each phase is the same, but the voltage to ground can vary depending on the load. If the loads on the three phases are not balanced, the neutral point can shift, causing some phases to have a higher voltage to ground than others. This can result in overvoltages on equipment connected to the system, potentially damaging sensitive electronics or causing insulation breakdown. Transients, such as lightning strikes or switching surges, can also cause neutral point shift. These events can create temporary voltage imbalances that can stress the electrical system. To mitigate the effects of neutral point shift, several measures can be taken. Firstly, it is important to balance the loads on the three phases as much as possible. This can be achieved by distributing the loads evenly across the phases and by using power factor correction equipment. Secondly, surge protection devices can be installed to protect against transients. These devices divert excess voltage to ground, preventing it from damaging equipment. Thirdly, a grounding transformer can be used to provide a stable neutral point. A grounding transformer is a special type of transformer that is designed to provide a low impedance path to ground. It can help to stabilize the voltage on the system and reduce the risk of neutral point shift. Monitoring the system for neutral point shift is also important. This can be done using voltage monitoring equipment that measures the voltage to ground on each phase. If a significant neutral point shift is detected, corrective actions can be taken, such as adjusting the loads or installing a grounding transformer. The importance of proper transformer connections cannot be overstated. Transformers are essential components in electrical power systems, used to step up or step down voltage levels to efficiently transmit and distribute electricity. Correct connections are crucial for ensuring the safe and reliable operation of transformers and the equipment they serve. Incorrect transformer connections can lead to a variety of problems, including overvoltages, circulating currents, and equipment damage. In three-phase systems, incorrect connections can result in phase imbalances, which can cause motors to overheat and fail. One common mistake is improper phasing. Transformers have specific polarity markings to indicate the correct phase relationships. If the phases are not connected correctly, it can result in a short circuit or other serious problems. Another common issue is incorrect grounding. Transformers must be properly grounded to provide a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and energize the circuit. Incorrect grounding can increase the risk of electric shock and equipment damage. The NEC provides detailed requirements for transformer connections in Article 450. This article covers topics such as overcurrent protection, grounding, and clearances. It is important to consult the NEC and the manufacturer's instructions when connecting transformers to ensure that they are installed correctly. Regular inspection and maintenance of transformer connections are also important. Loose connections can cause overheating and arcing, which can lead to equipment failure. Connections should be checked periodically and tightened as needed. Infrared thermography can be used to detect hotspots caused by loose connections. When working with transformers, it is important to follow all safety precautions. Transformers can store large amounts of energy, even when they are de-energized. Always use proper personal protective equipment, or PPE, such as gloves and safety glasses, and follow lockout/tagout procedures to prevent accidental energization. Understanding voltage imbalance and its effects on electrical systems is crucial for maintaining reliable operation. Voltage imbalance, also known as voltage imbalance or voltage asymmetry, occurs when the voltages on the three phases of a three-phase system are not equal in magnitude or are not 120 electrical degrees apart. This imbalance can be caused by a variety of factors, including unbalanced loads, transformer problems, and open conductors. Voltage imbalance can have several negative effects on electrical equipment. Firstly, it can cause motors to overheat and fail. Unbalanced voltages create circulating currents in the motor windings, which increase the motor's operating temperature. This can shorten the motor's lifespan and lead to premature failure. Secondly, voltage imbalance can cause increased losses in transformers and other electrical equipment. The unbalanced currents create additional heat, which reduces the efficiency of the equipment. Thirdly, voltage imbalance can cause malfunctioning of sensitive electronic equipment. Many electronic devices are designed to operate with balanced voltages, and imbalanced voltages can cause them to operate erratically or fail altogether. The NEC recommends that voltage imbalance should not exceed 3%. This limit is intended to protect electrical equipment from the harmful effects of unbalanced voltages. Voltage imbalance can be measured using a voltage imbalance meter. This meter measures the voltage on each phase and calculates the percentage of imbalance. If the imbalance exceeds 3%, corrective action should be taken to reduce it. Corrective actions may include balancing the loads in the three phases, repairing or replacing faulty transformers, and correcting open conductors. Regular monitoring of voltage imbalance is important to ensure that it remains within acceptable limits. This can help to prevent equipment failures and maintain the reliability of the electrical system. The code requirements for transformers are detailed and extensive, covering various aspects of their installation, operation, and maintenance. These requirements are designed to ensure the safety and reliability of electrical systems that utilize transformers. The NEC Article 450 specifically addresses transformers and transformer volts. Some of the key code requirements for transformers include overcurrent protection, grounding, and ventilation. Overcurrent protection is required to protect transformers from damage due to overloads and short circuits. The overcurrent protection device, such as a circuit breaker or fuse, must be sized according to the transformer's rated current and impedance. Grounding is required to provide a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and de-energize the circuit. Transformers must be grounded in accordance with NEC Article 250. Ventilation is required to prevent transformers from overheating. Transformers generate heat during operation, and if they are not properly ventilated, they can overheat and fail. The NEC specifies the minimum ventilation requirements for transformers based on their size and type. Other code requirements for transformers include clearances from combustible materials, fire protection, and signage. Transformers must be installed with adequate clearances from combustible materials to prevent fires. Fire protection measures, such as fire-resistant enclosures or sprinkler systems, may be required for certain types of transformers. Signage is required to identify transformers and provide information about their voltage and other characteristics. It is important to consult the NEC and other applicable codes and standards when installing, operating, or maintaining transformers. Failure to comply with these requirements can result in safety hazards, equipment damage, and code violations. The role of impedance in electrical systems is crucial for understanding how current flows and how equipment is protected. Impedance is the total opposition to current flow in an alternating current circuit. It is similar to resistance in a direct current circuit, but it also includes the effects of inductance and capacitance. Impedance is measured in ohms and is represented by the symbol Z. Impedance plays a key role in determining the amount of current that flows in a circuit. According to Ohm's law, the current is equal to the voltage divided by the impedance, or I equals volts divided by Z. The higher the impedance, the lower the current. Impedance also plays a key role in protecting electrical equipment from overcurrents. Overcurrent protection devices, such as circuit breakers and fuses, are designed to trip when the current exceeds a certain level. The impedance of the circuit helps to limit the amount of current that flows during a fault, allowing the overcurrent protection device to trip quickly and de-energize the circuit. The impedance of a circuit is determined by several factors, including the resistance of the conductors, the inductance of the coils, and the capacitance of the capacitors. The resistance of the conductors is determined by the material, length, and cross-sectional area. The inductance of the coils is determined by the number of turns, their core material, and their geometry. The capacitance of the capacitors is determined by their plate area, their plate separation, and their dielectric material. In transformer applications, impedance is a critical parameter that affects voltage regulation, fault current, and efficiency. Transformer impedance is typically expressed as a percentage of the transformer's rated voltage. A higher impedance transformer will have better voltage regulation but will also have a lower fault current. A lower impedance transformer will have poor voltage regulation but will have a higher fault current. The selection of transformer impedance is a compromise between voltage regulation and fault current. It is important to choose an impedance that is appropriate for the application. Delta and Y configurations are two common ways to connect three-phase electrical systems. Each configuration has its own advantages and disadvantages, and the choice between them depends on the specific application. In a delta configuration, the three phases are connected in a closed loop, forming a triangle shape. There is no neutral point in a delta configuration. The voltage between each phase is the same, but the voltage to ground can vary depending on the load. Delta configurations are often used for power distribution because they can provide a higher voltage than Y configurations. They are also less susceptible to voltage imbalances caused by unbalanced loads. In a Y configuration, the three phases are connected to a common neutral point, forming a Y shape. The voltage between each phase and the neutral point is the same, and the voltage between each phase is 1.732 times the phase to neutral voltage. Y configurations are often used for power generation and transmission because they can provide a stable neutral point. They are also more efficient than delta configurations because they have lower losses. The choice between delta and Y configurations depends on several factors, including the voltage level, the load requirements, and the desired level of reliability. In some cases, a combination of delta and Y configurations may be used to achieve the desired performance. Single phasing is a condition that occurs in three-phase electrical systems when one of the phases is lost or disconnected. This can happen due to a blown fuse, a tripped circuit breaker, or a broken conductor. Single phasing can have several negative effects on electrical equipment, especially motors. When a three-phase motor is operated on single-phase power, it will not start. If the motor is already running, it will continue to run, but it will operate at a reduced speed and with reduced torque. The motor will also draw much more current than normal, which can cause it to overheat and fail. Single phasing can also damage other electrical equipment, such as transformers and generators. The unbalanced currents caused by single phasing can create excessive heat, which can lead to equipment failure. To protect electrical equipment from single phasing, several measures can be taken. Firstly, overcurrent protection devices such as fuses and circuit breakers should be sized correctly to protect the equipment from overloads and short circuits. Secondly, single-phase protection relays can be installed to detect single phasing conditions and trip the circuit breaker. Thirdly, phase monitors can be used to monitor the voltage and current on each phase and alert the operator if a single phasing condition occurs. Regular inspection and maintenance of electrical systems are also important to prevent single phasing. Loose connections, damaged conductors, and faulty overcurrent protection devices should be repaired or replaced promptly. Understanding harmonics in electrical systems is essential for maintaining power quality and preventing equipment damage. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. Harmonics are generated by nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces. Nonlinear loads draw current in a non-sinusoidal manner, which creates harmonic currents that flow back into the electrical system. Harmonics can have several negative effects on electrical equipment. Firstly, it can cause overheating of transformers, conductors, and other equipment. Harmonic currents create additional losses in the equipment, which increases its operating temperature. Secondly, harmonics can cause malfunctioning of sensitive electronic equipment. Many electronic devices are designed to operate with sinusoidal waveforms, and harmonics can cause them to operate erratically or fail altogether. Thirdly, harmonics can cause resonance in electrical systems. Resonance occurs when the harmonic frequency coincides with the natural frequency of the system, which can amplify the harmonic currents and voltages. To mitigate the effects of harmonics, several measures can be taken. Firstly, harmonic filters can be installed to block the harmonic currents from flowing back into the electrical system. Harmonic filters are typically composed of capacitors and inductors that are tuned to specific harmonic frequencies. Secondly, harmonic reducing transformers can be used to reduce the amount of harmonics generated by nonlinear loads. Thirdly, power factor correction equipment can be used to improve the power factor of the system, which can also reduce the amount of harmonics. Regular monitoring of harmonic levels is important to ensure that they remain within acceptable limits. This can be done using harmonic analyzers, which measure the amplitude and frequency of the harmonics. The significance of voltage regulation in electrical systems cannot be overstated. Voltage regulation is the ability of an electrical system to maintain a stable voltage under varying load conditions. Good voltage regulation is essential for ensuring the proper operation of electrical equipment and for preventing equipment damage. Poor voltage regulation can result in several problems, including voltage sags, voltage swells, and voltage flicker. Voltage sags are temporary decreases in voltage that can cause equipment to malfunction or shut down. Voltage swells are temporary increases in voltage that can damage sensitive electronic equipment. Voltage flicker is a rapid fluctuation in voltage that can cause lights to flicker and can be annoying to people. Several factors can affect voltage regulation, including the impedance of the electrical system, the load characteristics, and the presence of voltage regulators. The impedance of the electrical system is the total opposition to current flow, which includes the resistance and reactance of the conductors, transformers, and other equipment. The higher the impedance, the poorer the voltage regulation. The load characteristics also affect voltage regulation. Loads that draw a large amount of current can cause voltage sags, while loads that generate a large amount of reactive power can cause voltage swells. Voltage regulators are devices that are used to maintain a stable voltage under varying load conditions. They work by automatically adjusting the voltage to compensate for changes in a load. There are several types of voltage regulators, including tap-changing transformers, step voltage regulators, and static volt-ampere reactive compensators, or static volts-amps reactive, or StatComs. Regular monitoring of voltage levels is important to ensure that the voltage regulation is within acceptable limits. This can be done using voltage monitoring equipment, which measures the voltage at various points in the electrical system. The consequences of improper grounding and bonding are severe and can lead to dangerous situations. Grounding is the process of connecting non-current carrying metal parts of electrical equipment to earth, providing a low impedance path for fault current to flow back to the source. Bonding is the process of connecting together all metal parts of the electrical system to ensure that they are at the same electrical potential. Improper grounding and bonding can result in several hazards, including electric shock, fire, and equipment damage. If a ground fault occurs in a system with improper grounding, the fault current may not flow back to the source, and the overcurrent protection device may not trip. This can create a dangerous situation where the metal parts of electrical equipment become energized, posing a risk of electric shock to anyone who touches them. Improper bonding can also create a risk of electric shock. If the metal parts of the electrical system are not properly bonded together, there can be voltage differences between them. This can create a shock hazard if someone touches two metal parts that are at different voltages. Improper grounding and bonding can also increase the risk of fire. If a ground fault occurs in a system with improper grounding, a fault current may flow through unintended paths, such as building steel or gas pipes. This can cause overheating and arcing, which can lead to a fire. To prevent these hazards, it is essential to ensure that electrical systems are properly grounded and bonded in accordance with the NEC. The NEC provides detailed requirements for grounding and bonding in Article 250. Regular inspection and maintenance of grounding and bonding systems are also important to ensure that they are functioning properly.